Hello, welcome to our first digital lecture. I miss all of you. I hope that you're doing very well and that you're staying healthy and that you are social distancing and, of course, washing your hands. But today we get to start our last topic of the year, marine biology. And to start the topic of marine biology, we absolutely have to start with the ocean. So today we are going to investigate and learn about different properties of the ocean. Because life on our planet would absolutely not be able to exist without our ocean. So by studying how ocean life operates, we can then just ensure and maintain the health of that ocean life. And then we can make sure that our planet functions as it should, so that our life on land is going to be able to operate correctly. Again, going back to homeostasis, keeping everything in balance is absolutely what life needs. So, the objectives then for today for this lecture, number one, so that we can figure out different types of properties that ocean has. So, chemical properties that the ocean has that supports and sustains life. We will also be talking about different types of oceanography tools, so that how we can survey and know what those chemical properties are. We'll get into a little bit on ocean geography, and then that influences how waves move. So we'll also then get into tides and the forces then that tides have. So in order for you to follow along with this lecture, you can of course take pencil paper notes, but you can also open up the document that's on Schoology, that is a Google Doc, and you can use that to follow along. So let's get started. First, the different physical characteristics then of an ocean. Well, the ocean is going to make up about 3/4 of our entire planet. So if we were to look down from space, we would see mostly ocean in terms of what that view would be. The ocean water itself is going to be made primarily of two things: water, so 96.5%, as well as salt, so NaCl, it's about 1%. Now there are some other things then that are going to be dissolved within the water, so different types of ions that are also dissolved, but the primary one is NaCl. The water itself, the top part of the water, is going to be heated by an infrared wavelengths of light that come from our sun. The bottom, the ocean depths, are usually very consistent, right around 2 degrees Celsius. It doesn't change if you go from the Arctic to the tropics. It's all about the same. And the fortunate part then as well is that there's liquid water, so it's about 4 degrees warmer than the freezing point that salt water has. So again, it's got a different freezing point than fresh water would. And then the density of salt water is 1.026 grams per centimeters cubed. And that's going to be a different density than the fresh water that we have on our planet. The fresh water that we have on our planet only makes up about 2.5% of the entire water that we have. So most water on our planet is seawater. That makes up about 97.5% of the water that we have on our planet. So where do the temperatures actually change? So if we were to survey different depths of the ocean environment and then figure out the temperature of them, the top 100 to 300 meters is going to be the area of the ocean that does have mixing occur. So that's going to be heated by the infrared wavelengths, and that's going to be able to have different temperatures than the depths of the ocean that do not see any of that sunlight. So the top is a seasonal mixture. So depending, again, if we think of if you were to go to the Jersey Shore, May versus June, August, it's going to have different temperatures, although they don't vary too drastically, but there is warming that does occur. So that's going to happen up there in the mixed seasonal layer. But then after you reach about 300 meters, you're going to start to experience a thermocline. A thermocline then is going to be this sudden change of temperature. So as you go to the lower depths, that temperature is going to decrease for the most part, unless, let's say, you're started with a really cold Arctic ocean to begin with. And then you will reach your deep ocean, which again has that temperature of about 2 degrees Celsius. Some of the other chemical characteristics, like we noted, that salt makes up about 1% of the salt water. Water makes up a significant part of them. And then there are also some other minerals that do make up most of that sea. But besides that, you are going to have other compounds, so gases that will be dissolved within the ocean water, carbon dioxide, oxygen. If we think about the different types of consumers and producers, they're going to be expelling those gases. Also nitrogen that can be mixed in with that environment. And a lot of that too can come from organisms, from their nitrogen waste, or from the atmosphere itself. So where does all the salt come from? If you were to notice that salt water is salty, where does that salt come from? Well, it comes from rocks on land. So what happens is as rain falls, it is going to bring with it carbon dioxide that we have, that all organisms expel. That carbon dioxide, when it mixes with water, forms carbonic acid, which does lead to acid rain. So the rain falling from the sky, and this can happen more so in different places, but it is going to be acidic. So that acid slowly over time is going to erode the rocks that we have on land. Those rocks, when they erode, they are going to turn into ions. So little pieces of the rock coming off at a time, forming ions. Those ions then through runoff are going to be put into streams and then to rivers through the watershed, and eventually will lead out to the ocean. And then in the ocean, they can be used, and many of them are used by living things, but there are ions that do not get used. And then slowly over time, those concentrations have built up to the salinity level that we now have today. So the two most prevalent ions then that are going to be found in the ocean are chlorine and sodium. So together they're going to be those salty, table salt, NaCl. The concentration of salt in an ocean is about 35 parts per thousand. So if you were to weigh out or take the salt out, it would make up about 3.5% of the weight of seawater. And it was also estimated if you were to take out all of the salt from the ocean and spread it across all of the land that we have, it would actually reach the height of about 500 feet, which is about the height of a 40-story building. So there's a lot of salt packed into our oceans. So how do we know all of these different types of chemical processes or chemicals that are going to be found within the ocean environment themselves? There's simple tools that oceanographers, marine biologists will use in order to find out things like pH and salinity level and the concentration of debris within the ocean environments. These that we're about to go over are ones that we would use for our Wallops Island trip. So hopefully we can still get that in. Hopefully it can be rescheduled. And this would be part of the boat excursion that you would actually get to use several of these that we'll go over now. So the first one is the Nasson bottle. The Nasson bottle, it looks just like this picture. So it usually is this yellow bottle. And then there are valves at each end of the Nasson bottle. You would close one of the ends. And the one that you would use at Wallops is just one Nasson bottle, not the series like that's shown here. You close one of these and then they're attached to the rope. There is different measurement markings. So if you want to measure it 5 meters or 10 meters or 15 meters, then you would lower down this bottle until you got to that knot, which would signify the distance that you are measuring. Then you release the messenger. So it's a little metal piece that travels down the rope. It will hit one of the valves, it will close that valve, and then it will make it so that that water gets trapped within there. So then by measuring different samples, you can measure these things we're about to go over at different depths. So you can see how concentration or temperature or pH might differ at each of these depths. A refractometer is going to measure the salinity. So you are going to put a drop of the seawater on the prism. You look through the eyepiece, and then you can actually see this line, and this line will be able to determine how much salt is found within that water sample. pH test kit, very similar to ones that you have used before. This one has the general indicator that you'd put into the water. You could also use those standard pH test strips, but that's going to measure then the concentration of hydrogen ion. So depending on if it has a lower or greater amount of hydrogen ion, it's either going to be more basic or more acidic. And again, going back to life and homeostasis, organisms are going to need a stable range of pH, just like everything else. So it's important then to know the pH of water. So again, besides water and salt, there are other gases that are going to be dissolved within the ocean environment. And if we think of oxygen, well, most organisms are going to need oxygen to survive. So again, seeing how much oxygen is dissolved within the water, you can then make a note and see how then organisms might respond to any change that would happen. It tends to have much less oxygen that's dissolved within water than an atmospheric oxygen. So organisms are going to have a continual flow of water, maybe over their gills, so that they can collect enough oxygen. But what happens here in this test kit is you collect your water sample, and then you go through a series of chemical steps to fix your sample, and then you can, through a titration, figure out how much oxygen is dissolved per parts per thousand within your water sample. A SECCHI disc is used to figure out how transparent the water is. So if you were to go, let's say, on a vacation that would hopefully happen in June, or a vacation that may happen later in the summer with your family to a Caribbean island, you would notice a big difference between maybe the water at Wallops versus the water at Punta Cana. The Caribbean environments, they tend to actually not be as healthy. So there's going to be a higher temperature. There may not be enough organic material for those fish to eat. So if we were to look at the crystal clear waters of the Caribbean, those are not going to be as healthy or as diverse ecosystems as the Jersey Shore or Wallops Island would be. So it's much more green, browner from the different types of algae and organisms living within that. But it can also then measure how much productivity can occur, or how turbid that particular area is. So the more light that can get through, then theoretically the more production you could have of your plant species or algae species. So what you would look for then is the depth at which you could actually see this disc. So it's kind of like a checkered pattern, white and black, and then you can measure to see how far that light is able to penetrate. A Forel-Yule color scale you can use then to actually quantify the color that you're seeing. So instead of saying like blue or light blue or turquoise or brown, this one will actually give you a quantifiable measurement that you can use to describe the color of the environment, the marine environment. And then again, that can correspond with the types of organisms that are living in that area. Plankton nets. So it's a really fine mesh net that you put along the side of the boat. And as you move, it's going to collect those really small plant and animal plankton. Those plankton are just any organism that cannot fight the current. Most of the time they are small, but they don't actually have to be. They can just be any type of organism that doesn't have a means to propel itself against the current. So typically it is towed on the side of the vessel or behind the vessel, and then you would collect your specimens. Right here at the bottom, there tends to be an opening in which you can collect specimens with. Next is the bottom shippic grab, or also known as the benthic grab. benthic refers to the bottom layer. So this collects organisms off the bottom of the ocean floor, just like you might for a claw machine. It kind of looks like that here. Then what you would do is, again, take that back to the lab, just like you would with the plankton net. And then you can look at the organisms that you have collected on that are living right at the bottom of that ocean floor. And through the benthic crab, the plankton net, and the otter trail, or otter trawl, those can all be used to measure biodiversity. And with biodiversity, you absolutely want the most diverse life that you can, and that's going to show you a really healthy sign of the marine environment. A current cross is going to be used to determine the speed and direction of tidal currents. So you would release this, and then you would see how long it takes for this to get to a certain length. So you would then be able to figure out your velocity based upon how quickly that was able to travel. So your distance divided by your time. And then you can also look to see which way it goes, and then you can figure out the direction of those tidal currents. So with all of these then that we went over, they're going to measure either ecosystems at that moment, so temperature, pH, dissolved oxygen, but you can also measure the ecosystems over time by measuring and seeing those different organisms that you collect. And then that's going to give you a really good indication as to the state of that marine ecosystem.